Hello everybody, up games, and welcome to a tutorial on simple genetic algorithms in Unity. And yeah, without further ado, I'll just show you what I'm gonna be building today, and I'll talk a little bit about genetic algorithms in general while it runs. So what is a genetic algorithm? They're usually used to solve a problem, some kind of problem, and in this case the problem is to get from the blue cube to the red cube without colliding to obstacles. And yeah, each of these guys are like the algorithm consists of a population, as you can see, all these guys, and each of these guys has a genome or DNA associated with them. And in this case, the DNA is just an array of vector 2s that tell them where to go. It'll just run through the list and move them to each position and draw a line behind them. And like after each round is completed, it will check which creatures did the best, cross over those creatures' genes and mutate them a little bit, and then spawn new creatures and with the new genomes and run it again. And in a little while they will probably get to the red cube. There, as you can see, they have hit a little bit of a bottleneck, but they will get over it soon. And yeah, like, let's just let it run for a little while. I'll open up a new scene and start coding things. And like, if you are familiar with arrays and know how to deal with lists and stuff, you'll be okay with this one. It's pretty simple stuff. Yeah. So open up a new scene here, empty scene, and get started. Yeah, as you can see here, I have an empty scene. I only have these two sprites that I'm going to use for this. I will provide a download link for this whole project once I'm finished. Don't worry. And let's just create a new folder called scripts. Just gonna be writing some scripts. I'll just turn the main camera background to nice dark black. Increase the camera size. Yeah. Let's just create a couple sprite objects. I'll just drag two of these cube blocks here. Just decrease the size a little bit. Yeah, better. And let's name one of these target. And with one of these spawn point. Color this one blue. And the target red. And yeah, as you can see, we have the same situation without the obstacles here. And let's just create a couple C# scripts now. First we're gonna create the genetic pathfinder, which will be our creature. And a population controller, which will be handling our population and all that stuff. And let's just create one more script called DNA. You probably wouldn't really have to do this for this kind of simple scenario, but I'll just create it anyway. And let's just open up the DNA script for first and create this stuff. Yeah. Just delete all this stuff. And this will not inherit from the monobehavior class, so we don't need that. And yeah, what we're gonna need, we're gonna need a public list of vector 2s called genes. It's gonna equal to a new list of vector 2s. And then we will create a couple of constructor constructor functions. So say public DNA, and this will take in an integer. It's called genome length. We'll just default that to like 100 or 50. We'll only use 50. Don't need that much because it's such a simple scenario. And then we'll just create random vector 2's for each of these. So we'll make a for loop. So for int I is equal to 0, I is less than genome length, I plus plus. And then we'll just say genes.add new vector 2, and we'll just make it random, the range to get a random value, and we'll just say minus 1.0 f and 1.0 f, and just copy that for the y coordinate. Yeah, so here we're just looping through the looping for 5 times or 50 times, 40 times with genome length. Then we're adding any random vector 2 to our genes list. Okay, and then we're gonna create another constructor, and this one will take in a DNA called parent and a float called mutation rate. And so this constructor will be the class we will pass our last DNA through to get our child's DNA, if you understand what I'm saying here. Yeah, and so we'll just default the mutation rate to something like 0.01. It's a nice small mutation rate for starters, and we can, like, because I'm defaulted them here, we don't have to type it in when we're calling this constructor, but we can if we want to. So for the parent, we're gonna make another for loop. So I'll just copy this last one, but instead of adding a new random genome, we're gonna this is gonna be changed to parent.genes.count. So we get the same amount of genes, and instead of adding new random one, we're gonna add the parent's gene at that index. But first we're gonna check, so we're gonna make a float mutation chance, and that's gonna equal to a random.range, and we're gonna say 0 to 0.0. So, and then we're gonna check if this mutation chance is less than our mutation rate, and if it is, we're gonna make a random gene, and if it isn't, we're gonna copy the parent gene. So that's how we're gonna get the mutation ins. So let's just write if mutation chance is less than mutation rate, let's make it less than equals to, then genes.add new, let's copy this one, paste it here, so new random vector 2 else genes.add parent.genes I. There we have it, with the mutation. And then we're going to create another one, because if we want to have a crossover, we're gonna have to make a crossover one, but this is only if you want to make like without the crossover. Or let's just make it with the crossover here. Let's not make things too complicated. So let's take an error in DNA, and that's gonna be other parent, or like partner. Let's say partner. And then here we're gonna make an error in chance is equal to random that range 0 2, and it's 0 2 because these are integers, and the integer random that range is exclusive, so this is going to be going to 0 to 1. And then we're going to say if chance is equal to 0, we're going to add the parent genes that else we're going to put genes that add partner genes. Yeah, and this is going to be just like it's going to randomly cross over each parent genes. We could do like a crossover point, like pick a random point between like 0 and 50 and take half of the other parents half of the other, but I prefer doing it this way. I don't know why, I just like it more. And it's basically the same thing, it's just crossing over some of the DNA. And it's gonna work for this scenario. And yeah, there we have our whole DNA class. We don't really need anything else there. And there's the whole thing, and let's just save that. Then save the genetic pathfinder, and this is gonna inherit from the mono behavior, but let's just take these out for a second. And the genetic pathfinder class will have a DNA called DNA, and it will have a void initial init creature, something like that. We're gonna make two, and it's gonna be a public void, and we're gonna make two initialized creatures. One with just create the random one, and one with the crossover, because the random one is going to be used for the first generation, and the other one is going to be used for all the subsequent generations after that. Which is, before we create that init creature, we're gonna put in like some stuff like boolean has been initialized. That will equal to false by default, because we will change to true when the creature has been initialized. That's how the creature will know when to start to execute its stuff and go through its DNA. Then we're gonna create a transform, or let's just create a vector 2 target. Vector 2, next point. Let's make another boolean. Oh, it's the D. Damn. Boolean called has finished. That will be called false also. Yeah, we will add some more stuff later, but this will do for the beginning. Target, beginning, yeah. Let's just add a float called creature speed. It's gonna be a public float, so we can change it in this vector, and then a public float. Let's make a, what should I call this? Path multiplier, because each vector in the path is going to be multiplied with this when executed, and with changing this we can get different kind of movement, but like, yeah, you can play around with that. Yeah, let's get to our initialized creature. So this will take in, once again, integer genome length and the vector2 target, and let's just make it underscore target so we don't get confused. And then here we can say DNA is equal to new DNA genome length and target is equal to underscore target. And we'll also say next point is equal to transform.position. Yeah. Then we just make another public void init creature, and this one will pass in just a DNA called new DNA. Oh, we could actually, we don't need this other one. I just realized we can just pass in a new DNA because we can in the simulation controller, what was it called again? Population controller file, where we can just create a new random one when we start. So we don't actually need, we only need one of these. So DNA is equal to new DNA. Yeah, that's our init creature. Then we'll make a void update. And in the update, we will say if has been initialized. So it will only run if it's been initialized, if this one is true. And yeah, so we have to make stuff to make the next point match our DNA, and we have to make an integer called path index, and that will fall to 0, and this is how the creature will know, or we will get the right vector in our gene array thingy in our DNA class. So if we're gonna say if transform.position is equal to the next point, we'll have to cast this to a vector2 like so. If transform.position is equal to next point is equal to transform.position, again cast this to a vector2 plus DNA.genes path index, and then we will increment path index plus plus, like so. Else transform.position is equal to vector2 that move towards, so the position to get our current point and next point to get our target, and let's put in our creature speed times time dot else time. And to test it out, we just create a start function just for a second here, and we'll call init creature new DNA. Let's just put 50, or it has that, we don't need. Put it in. The target will be, let's just put like 0 point. We will try to find the center, because I have to put in, it doesn't do anything with the target position. before this, we'll just check if path in path index is equals to DNA.genes.count. We'll just make a end function. Oh shit. No wait for end frame, I just want end. Okay, let's just create the function first. End, call it end here, and we'll say has finished is equal true. We'll just say and not has finished. Yeah, so this will run only if the creature has been initialized. We need to change this to true here in the initialized creature, so it will start. Then it will run through its genome until it gets to the end of the genome, and we'll just test it out on the scene first so that we know that it works. Put in one of these, so that's so small. Well, no worries. Let's just put genetic pathfinder object on that. Let's put the creature speed to something like 10, path multiplier to 2, and let's just run it. Yeah, and as you can see, our creature is moving around randomly until it gets to the end of its path. Just like we wanted to. So that works splendid. And then we'll just delete this one because we don't actually want to do it in the start. Yeah, then we'll create something like fitness that returns float, and then it's a public float fitness. This should be a getter. We don't need to set this. Let's say return 0 first. Yeah, we're gonna say float this is equal to vector2 dot distance transform the position and target like that, and we'll just return like 60 divided by distance, so we get the inverse. Like the closer the creatures are to the target, the higher their what's that called? Fitness will be. And then before we return, we have to check, because if the creature is on the target point, this will make a division by 0 error. So we don't want that. So we say if distance. Oh, let's make this inverse distance. Let's return that. No. Let's go back. That's distance. If distance is equal to 0, we'll just say distance is equal to 0.001 or something small like that. so that we don't get a division by 0 error. That should work for now. We're gonna improve on the fitness function a little bit in later on, but that should work for now to get our fitness. And we don't actually need to have an end function. We can just say has finished is equals to true. Know what I was thinking there? Yeah, there we have our creature for now. Then we will start to work on our population controller. Class, and this will always also inherit from one behavior. It's going to be in the scene. So here we will make a list of genetic pathfinders called the population. Population. That will be equal to new list genetic pathfinder. And then we'll have a public integer called population size. That will equal to default like 100, and then like public float cutoff. This will determine like how much of our population will survive and how much of them will die, how many of them will die. And this will be equal to something like 0.3 for first. We can change this, play around with this, and have different kind of results. And the larger the population is, the better chance that there is creature or genome mix that will actually solve the thing you're trying to solve. So the larger population will always get better results, but a larger population means more stuff on your screen also. So here we just make a void init simulation. Alright, let's just play population. So we call it the population controller. Called my last one the simulation controller, so that's why I made that. And in our init population, we'll just say for int I is equal 0, I is less than population size, I plus plus, square brackets, and we'll also need a public game object, and this will be our creature prefab that we're gonna spawn in the scene. So we're gonna say game object go is equal to creature prefab. Oh no, it's gonna be equal to instantiate creature prefab, and then we'll need a transform start, public transform start, public transform end. So we'll have the spawn point. Let's just call this a spawn point for simplicity's sake and understandability's sake. Oh yeah. And then we'll just spawn this at the spawn point and just putting quaternion dot identity spawn point that position. Yeah. And let's say go that get component genetic pathfinder, and let's just add that to the population like so. Population that add all that stuff. Then we have that. There we have our initial. Oh, I forgot. We have to go that component genetic pathfinder dot unique creature, and we're gonna pass in a new DNA. And here we're gonna have a public integer called genome length. And pass that in the new DNA. We don't have to do that, but we're gonna do that, and then just pass in the end that position, like so. So that's our population initialized, and then we get to doing the crossover with our DNA class. If you remember all these things here, this constructor mostly. Yeah, so then we create a void called next generation. Also have to create a boolean called has active. Let's create that first so we can check if we have active creatures still, and if we do, we won't spawn the next generation or do the crossover. We will wait until we don't have active, or like all the creature have finished. So in here we just say if let's just say for int I is equals 0, I is less than population dot count I plus plus, and then we'll just say if population dot I dot we'll have to make these has finished boolean the public one. Has finished, and we'll have, if it's not finished, we'll return true. Return true, and if it loops all through all of them and none of them return true, then return as not finished, then we'll just return false. Yeah, then let's get to the next generation, and I think this will be like the hardest part, and it's not super hard in my opinion, but like depends probably on your skill level. Yeah, so let's get to it. So we'll determine the cutoff by doing integer let's just call this survivors is equal to population size times the cutoff, and we'll just say, because this will be a float, we'll just say mathf that round to int. We could have just cast it into an integer too, but rounding is better in my opinion. And then we'll just say we'll create a new list, a list of genetic pathfinders called survivor. Let's call this integer survivor cut, and this list we'll call survivors. And that will equal to new list genetic pathfinders. And then we'll also have to create. Forget about that. We have to create another thing that returns a genetic pathfinder. Go get fittest. It will make like max float max fitness. That's equal to float minimum value and an integer index that's equal to, say, -1. And then let's say 0. 0 is good. For int I is equals 0, I is less than population dot count I plus plus. Not what I meant to do. That's what I meant to do. Just say this. Then inside the for loop, we'll just say if population dot I dot fitness is more than max fitness is equal to population I dot fitness and index is equal to I. And after the for loop, we'll just say population dot let's just say genetic pathfinder fittest is equal to population index, and then under that we'll just say population dot remove fittest, so we don't get the same fittest every time. And then after that we'll just say return fittest. So now we get back to the next generation function here, and we'll just say for int I is equals 0, I is less than survivor cut I plus plus, and then we'll just say survivors dot add fittest, get fittest. Yeah. After that, we can destroy every game object in the population that remains in the population. So we just say for int I is equals 0, I is less than population dot count I plus plus, and then inside that we just say population destroy. Population I, and after that we just say population dot clear to clear the list. And after that we have the mating. So we'll just say we'll make a while loop. So while population dot count is less than population size, we'll do this, and inside this we'll just say and make for loop for int I is equals 0, I is less than survivor cut I plus plus. No. Let's say survivors that count. And that would have worked too, but let's just do it this way. I prefer to actually see what I'm dealing with. So let's just say game object go is equals to instantiate where was creature prefab at spawn point, and then we'll just say quaternion.identity position. And then we'll say, oh, that component, genetic pathfinder, the init creature, and now we'll pass in new DNA called, and it will take in survivors i.dna. Is it not a public one? Yeah, okay. I should make this public. Public DNA. And then we'll, yeah, survivors DNA. And we'll say survivors. And here, inside here, we'll say the square brackets will say random and range 0 to 10. I'm not gonna do a complicated cutoff thing. It just picks the random from the top 10 creatures. .dna, and then we'll just after that we'll the new DNA will pass in our end that position, and then we'll just say population dot add go dot get component genetic pathfinder. Oh, this video is getting super long. Genetic pathfinder. And we'll just say if population dot count is equal to more than equal to population size. Let's just break out of the loop. And then finally we'll create a void start. We'll say unit population void update. We'll say if not has active next generation. Oh, I forgot I have to loop through for int I is less than survivors dot count I plus plus. Here we're gonna say destroy survivors dot game object survivors I dot game object. Yeah. Oh, and in here destroy population I dot game object. You have to remember that we have to destroy the game object. Yeah. This should work now. We'll just create a simulation controller object. Let's call it population controller. And yeah, let's just parent put these as child objects, and let's just add the population controller. We'll make this prefab. Just create a folder called prefab. Probably should have called it prefabs, but in this case we only have one prefab at the moment. And I'm gonna make this two-parter because this video is getting so long. Just dragging the spawn point and the target point, like 50 genome length, cut off. Yeah. Dragging the creature prefab we just created. I'll actually gonna go to the Gene Pathfinder and say, or here, or if the path index is DNA.genes as count, or transform that position, let's just say 32, the distance, transform that position, endpoint target is less than 0.5. So if it's close enough to a target, you can say that it has finished and reached the target. Yeah, let's just run this now and hope everything works. Let's increase the creature speed to like 50 so we can see a little bit faster. Evolution. And yeah, a little by little they should get better at getting to the target. Just make the path multiply a little bit bigger. Genome a little bit longer. Increase the population just a little bit so we can have a better gene pool. As you can see, they're just at first they're randomly moving, and then they will slowly convert to better creatures. So it kind of works. Of course, like, if I had more time, I could make this better, and in the next episode we will make this better. We will get to the point, in the next episode we will probably finish and get to the point that I was in my example project that I showed in the beginning. Yeah, it's Up Games, and I hope you learned something, new. I hope my explanation wasn't terrible. And if you enjoyed or learned something or stuff, leave a comment and like this video. And I will be back with the next episode sometime soon, probably in a couple of days, or maybe today, later. But hey, thanks for watching. See you next time.